So in the last few lessons, we've been looking at transfers of energy, so energy going from one store to another store. But really, we've been talking about energy transfers that are useful, the energy transfers that we want to happen. So for example, the chemical store of energy in the petrol in a car is transferred into kinetic energy to make the car go forward, and that's useful because we want that car to go forward. It's what we want to happen. Or a boy using a slingshot, the elastic energy in the stretch rubber band is transferred into the kinetic energy of the stone, and we want that stone to go and fly, and so it's useful. But energy transfers don't always happen in exactly the way we want to. Usually when energy is being transferred, some of that energy goes to how we want it to, but quite a lot of the energy gets transferred in a slightly different way that is less useful. So for example, if we go back to that car, we're taking the energy from the chemical store and we are transferring it into kinetic to make the car go forward, but some of that energy from the chemical store isn't being transferred into kinetic energy. Some of it gets transferred into thermal energy. If you've ever touched or felt an engine after it's been running, you'll feel it gets very, very hot. So some of the chemical energy is transferred into thermal energy, and that heats up the engine and it heats up the environment. That's not useful to us anymore. It spreads out into the environment and we can't use it anymore. That spreading out of energy into the environments that we can't use it, that is called dissipation. So you can see this is a thermal image of a camera. So the blue areas and the black areas are cold, and the yellow ones are getting a bit warmer. The red areas are hot, and the very, very hottest are the white areas. So this is a car after it's been driving. You can see the engine got very, very hot. So lots of the chemical energy being transferred into thermal energy there. You can see through the tyre there more spots of white where the engine is very, very hot, but the tyres themselves also get quite hot, that dark red colour, because of friction with the road. So the road also gets heated up a bit, and again that is energy that is being wasted, that we're not using in the way we want it to. So energy can be wasted in other ways as well. So for example, not only does the car cause the surroundings to get warm, it also makes quite a loud noise, and so those sound waves also transfer some of the energy from the chemical energy store that we would rather went into the kinetic energy store of the car, that we would rather was used to make the car go faster. Now, some cars are more efficient than others, and that means that more of the chemical energy from the petrol is used to make the car go faster, rather than heating up the surroundings or rather than making a loud noise. So if we look at these two cars here, this car is quite sleek and smooth and thin and close to the ground, so when it's moving, the air goes over it and there's less resistance from the air causing heating up, and so more energy lets that car go forward. With this car here, lots of the air is going to be hitting it, causing some of the energy to be transferred into thermal energy and less of it being transferred into kinetic energy. So this car will be more efficient than this car. We're going to spend most of this lesson looking at efficiency and how to calculate efficiency. I'm going to move over to the worksheet that you've got. And it gives you an equation. So we calculate efficiency by doing the useful energy output divided by the energy input. So how much of the energy goes into the store that we want it to go into. So in the example of a car, how much of the energy is going into the kinetic energy store, divided by the energy input, so how much energy was in the original store, in the example of the car, this is how much chemical energy was stored in that petrol, and then we times it by 100 so that it is a percentage. I'm going to talk you through this first example, and then there are 3 for you to have a go at by yourself. So for each one, I'd like you to lay out exactly how I do for each of those ones. All right, efficiency equals, and the first thing we need to do is find the useful energy output. So it says a kettle that has an energy input of 100 joules and a useful energy output of 7 joules. So it says useful energy output is 7. So I'll write a 7 there. Divided by the energy input. So we need to find the energy input in the question. Has an energy input of 100 joules. And then we need to do our times by 100 at the end. And then I would say use a calculator for this one. Always use a calculator in science. There are no calculator paper, so always use one. Or use your phone if you need to. So use 7 divided by 100 equals, and then we times that by 100, which would give us an answer of 7. So the efficiency equals 7, and it's a percentage, so we write %. So have a go at the next 3 questions. I'm going to talk to the next part, so pause it and have a go at these 3, and then I'll move on explaining to the next bit in a minute. So the next thing that you need to do is to complete this table, which includes some data. So you have 3 columns that you need to complete. The first one is trying to work out how much of the energy has been wasted. So this is how much has been put in. This is how much was useful. So whatever the difference is between these two, that is how much is wasted. So to do that, and get your calculator out again, you take the input energy, in this case 3,600, and you take away the useful energy, and that will give you your answer. So in this case it is 3,000, lost my number there, I'm going to type it in again, 3,600 minus 108, 3,492 joules. So the first column is a nice easy subtraction. The second bit is doing the same thing that we have done up here. So you might want a scrap bit of paper. I know question 1 gives you a few lines there that you could use there, wherever you want to show you're working out. I'm going to write mine just in this space here. So efficiency equals, and so the first thing we need to find our useful energy output, and it tells you here the useful output energy is 108, and then you need your energy input, and it tells us here the input energy is 3,600, and then we times it by 100. And then use your calculator, 108 divided by 3,600 equals, and times by 100 equals 3. Now the last column I can't fill in yet for this row, because you have to wait until you've filled in all of these other 6 boxes, and you'll have to put them in rank order. So 1 will be the most efficient, so it will have the highest number in this column, and 4 will be the least efficient, so it will have the lowest number in this column. But you'll have to wait until you have all 4 of those answers to be able to do the rank in the last one. Now on the second page of this sheet there are some written questions. To answer those, you will need to go back to these pages, and you'll find the answers in here. So there's things like asking you to determine the or to state the equation for efficiency, which you'll find over here. And they ask you to describe what is meant by efficiency as well, which is up in here. So I have to look over here for the other answers. Now, if that has taken you the hour, that is fine. Stop there and submit what you have done. If you still have time left in the hour of this lesson, have a go at the summary question 1 that is over here. So a little bit of a challenge. If you still have time left and you are looking for even more of a challenge, have a go at question 2. So it's asking you to do more efficiency calculations. There, so it'll be a little bit more of a challenge.